Hi there. So we meet again. So for today I will discuss on example 8.5. Okay. So this one will involve interference, okay, due to thin films lah. Okay. So as we discuss the example, I explain a bit regarding the principle on how we use it or apply it to solve the problem lah. Okay. So this one example 8.5 over here, we have a non-reflective coating lah. Okay. So magnesium fluoride refractive index given 1.38, okay, and then it covers the camera lens, okay, given refractive index of 1.52. So basically when we have a non-reflective coating, okay, we will use a bit smaller value of refractive index lah, okay, compared to the medium itself, okay. So over here the non-reflective coating, okay, prevents the reflection of yellow to green light lah. Okay, so somewhere in between the spectrum of yellow to green. Okay, so the important thing is that the wavelength over here. Okay, so the wavelength is given as 565 nanometer, and then they want you to determine the minimum non-zero thickness. Okay, so the minimum thickness lah, okay, of the magnesium fluoride. Okay, so the information given. Alright, to simplify or to aid, what we can do is that we can draw a ray diagram lah. Okay, so this one will be much more better. Alright, so from the ray diagram, okay, so this is your incident ray. Okay, so once your incident ray hits the surface, it will be reflected lah. Okay, partially reflected and partially will transmit. Okay, so over here, since the surface of reflection has a higher refractive index, okay, so that means it will experience, okay, phase change lah. Okay, so over here you will have change in phase by pi radian, okay, and then the partially transmitted ray, okay, it reaches the medium N2 lah, for example, okay, and then it will be reflected also, okay. So over here, the medium of reflection over here, okay, has a higher refractive index 1.52 compared to 1.38, right? So that means this ray also will experience phase change, okay. So that means which will have a phase change of pi radian. Okay, now since the both experience phase change, so that means the reflected ray both will be in phase. Okay, so that means you will end up with coherent lah. Okay, so if we now, let's say we want to use drawing, so let's say you have an incident, so let's say this is your incident lah. Okay, incident. Okay, so over here the reflected ray 1, okay, reflected 1, so you have a phase change of pi radian, right? So phase change of pi radian, that means half of the oscillation. So that means the reflected will become like this. Okay, for A1, and then for A2, also you have change in pi radian, okay, phase angle. So that means reflected also will become like this. So that means for the reflected ray, both will be in phase. Okay, so in phase, that means m lambda, you will end up with constructive, okay, and m plus half lambda, you will end up with destructive lah. Okay, so over here they wanted to determine the non-reflective, okay, so prevent the reflection, so that means it should be destructive interference lah. Okay, so that means we will apply m plus half. Okay, so let us look into the solution. Okay, so for destructive interference, okay, so the equation you will end up with 2nt, okay, m plus half lambda. Okay, so for the minimum thickness order, we will take the minimum order lah. Okay, so the minimum order where we can have value. Okay, so over here, since it is m plus half lambda, zero order you still can have value lah. Okay, so that means which will end up with minimum thickness, because t over here, m over here, so that means t will be directly proportional with m lah. Okay, so add in the value, Okay, so we are going to determine the value of T, okay, minimum thickness. So which will end up with 102 nanometer. Okay, so this is an example for anti-reflective coating. Okay, next we look into reflective coating. Okay, so basically this one, a very simple example is that we have a soap bubble. Okay, so soap bubble, you have an index 1.3 in air. Okay, so the reflected light looks bluish. Okay, because the red light of wavelength 670 is absent lah. Okay, so that means 670 is absent, so that means it will become destructive lah. Okay, okay, so over here they wanted to state the condition and the minimum thickness. Okay, so for better understanding, like the previous one, okay, we can draw. So let's say when we have a soap bubble, okay, so this is your first ray. Okay, so the first ray is reflected at higher density medium. Okay, so that means higher refractive index. Okay, so once it is reflected at higher refractive index, you will have phase change by pi radian lah. Okay, now this is the bubble. Okay, we zoom the bubble. So let's say you have a bubble like this, okay, on a surface. Okay, so basically outside will be air and inside the bubble also will be air lah. Okay, so this is a bubble surface. So what we do is that we zoom out this part lah. Okay, you have air outside, this is a bubble, and then air inside. Okay, so for the second ray, it is reflected over here. Okay, where the refractive index is 1.0. When you have lower refractive index, you won't have any phase change lah. Okay, no phase change over here. Okay, so now let's say this one you have a phase change of pi radian, this one no phase change, so that means the sources will meet in antiphase lah. Okay, so let's say we have incident. Okay, incident. Okay, and then refracted one, you have phase change by pi radian. Okay, so this will be the reflected ray. And then for the second one, okay, you don't have any phase change, so that means you don't have any changes. So second ray will look like this. Okay, so that means it will meet in antiphase lah. Okay, so that means crest will meet with true, so that means you will have a destructive interference lah. Okay, okay, now for the condition, okay, the equation lah. Okay, where 2nt will be equivalent to m lambda lah. If you have m plus half, then it will become a constructive interference. Okay, and now for the minimum thickness, okay, previous one you can have m equal to 0, because m equal to 0 you will still end up with value. Over here you cannot have m equal to 0 because you won't get any value for thickness lah. Okay, so for minimum thickness, the m should be in minimum order where we can get value, so which will become as 1 over here. Okay, m will be equivalent to 1. So just replace in the value. Okay, so which will end up with the minimum thickness. Okay, so which you obtain 258 nanometer lah. Okay, so this is problem solving for involving thin film coating lah. Okay. Alright, thank you. That's all for today. Have a nice day.